Hey y'all, I hope you're having a good week. This week is probably the most intellectually challenging that we'll have in this course. And so that is going to be antiderivatives or integrals, right? Both of those are kind of interchangeable, and you will discover that in 5.3. So the sections we're going to look at are 4.9, which is antiderivatives, and then 4.1, 4.2, and 4.3, which is kind of your introduction to integrals, what those mean exactly, and then 5.3 is the fundamental theorem of calculus, which tells us how integrals and derivatives are basically two different sides of the same coin. In fact, they're exact opposites. So that is what we're going to look at. I'll try and be brief. Basically, we've been taking derivatives for a very long time now. Well, not very long time, like 3 weeks, but very long time in a mathematical sense. And so we just need to ask the question, what if we want to go backwards? So for example, if I take the derivative of x cubed, I use the power rule, bring the 3 down and subtract 1 from the exponent, I get 3x squared. So that's the derivative. If I start with 3x cubed, then I can go backwards. Right? I can undo the derivative. Right? Essentially, I can just add 1 to the exponent and divide by whatever that was. In this case, 2 plus 1 is 3. I divide by 3. The 3's cancel and I get x cubed. And so that is an antiderivative of 3x squared. Now you'll notice when I said the derivative of x cubed, I said the, meaning the only one. And when I said 3x squared, an antiderivative is x cubed. I used n, implying there's more than one. And that's because what if we took the derivative of x cubed plus 3? Right, the 3 would go away because it's a constant when we take the derivative. So we would still get 3x squared. So we have two functions that have the same derivative. So when we go backwards, right, we need to figure out exactly what we're doing there. And basically the way we get around that is we use a general constant, because it's always those constant terms that are the ones that can appear or disappear when it comes to a derivative. So if I were to take the antiderivative of 3x squared, that would be x cubed plus c. I would use c as what's called the constant of integration. And I would basically say, like, I took this antiderivative, this could be any number you want it to be, and this would still be true, so I'm just going to say in general, right, it's x cubed, that's the main part of the function, then plus some constant, plus c. So that's what you're going to look at first. Then you're going to move on to areas and volumes. And also, I'll just lump 5.2 in with that, the definite integral. So essentially what you're going to look at here, and this is the hard part. Okay, these are probably the two toughest sections in all of calculus. What you're going to look at there is you're going to try and answer the question, how do I find the area between a curve and the x-axis? So if I have a curve and I want to find that area, what do I need to do? Well, how you find that, right, if it's just a straight line, might be as easy as using a formula from geometry. If it's a wonkier line, then it gets a little weird. And so what we've done is decided, well, maybe I just need to estimate it, right? So I'm going to break that area up into rectangles. And I'm going to look at those rectangles, because I know how to find the area of a rectangle, and I'm going to add them all up, and that's going to give me an estimate. So maybe, like if I'm looking at an area between like 1 and 3, I'll just take 4 rectangles. So I'll have one rectangle that goes from 1 to 1.5, one that goes from 1.5 to 2, one that goes from 2 to 2.5, and then one that goes from 2.5 to 3. So I'll have 4 rectangles, and then I'll figure out the heights of those based on the function. So I'll draw the rectangles up to the top of the function. Now there's a lot of ways to do this, but there's two basic ways, right? We could use the left side of the rectangle and draw that up to the function. That's called using the left endpoints. Or we could use the right side of the rectangle and draw that up to the curve, and that would be the right endpoints. So either left estimate or right estimate, depending on what you use. Either way, what you're going to find is when you do this, the more rectangles you use, the better estimate you get. And if you draw a couple pictures of this, it starts to make sense as to why. There's less parts that you're either missing, if you're underestimating, and less extra bits that you have if you're overestimating. The more you use, the more accurate it's going to be. So then, of course, being calculus people, right, we would say, well, if we want the best estimate, then we just use all the rectangles. Now, using all the rectangles mathematically means taking the limit as the number of rectangles goes to infinity. So that's what we're going to do. We're going to take these rectangles, we're going to find the area of all these rectangles, we're going to add them up, and then we're going to take the limit as the number of rectangles goes to infinity. So basically we'll use like a generic number, like n rectangles, figure out what the area would be for n rectangles. That'll give us kind of a formula, and then take the limit as n goes to infinity. Now there's some notation you're going to come across here. You're going to find that you have a giant epsilon, and that is going to basically mean the sum of whatever follows. So you have a big old epsilon, and then you have a formula. And so the way that works, and it's best to read up on this, but I'll try my best to explain it here, right? You're going to start at whatever it tells you to. Usually it's n equals 1 to something, or I equals 1 to something. And then you will put the formula down. You'll substitute I, if it's I equals 1. You'll substitute 1 in for I. You'll have that part of the formula. Plus, it'll tick up. Now I is 2, so you'll copy the exact same formula, but plug in 2 for I, plus plug in 3 for I, plus plug in 4 for I, all the way down. So that's what you're going to look at for the sums. Those are going to help us figure out how to add up all these rectangles and give us a formula that we can use so we can take the limit as the number of rectangles goes to infinity. Now if we do that, that gives us the actual like straight up area under the curve, and we're going to call that a Riemann sum. But because mathematicians are lazy, we don't like to write that out all the time. So we have something called the integral, which is that weird S thing. So the thing that looks like this. And so that is our integral sign. And basically we're just going to rewrite our Riemann sums as integrals and look at them that way. And so that is the definite integral, meaning that we have bounds on it. So we're trying to find the area under a curve specifically from something to something else, 1 to 3 or 0 to 5, something like that. And that is essentially going to boil down to making a Riemann sum, trying to figure out what that is, what that formula is going to be, and then taking the limit as n goes to infinity. And that's frankly quite tedious. So this is where 5.3 comes in. We have something called the fundamental theorem of calculus, which literally is the most important theorem in calculus, why it's called the fundamental theorem of calculus. So definitely something you should know. And what this says is basically antiderivatives and integrals are the same thing. It also gives us a really nice way to evaluate out these definite integrals without having to do Riemann sums. Basically, we can find an antiderivative. So I find this new function, right? I have my function, I find the antiderivative, and I plug in my top bound for my definite integral, and then minus that same function, but I plug in my bottom bound. So you'll see this formula look something like the integral from a to b of f of x dx equals capital F of b minus capital F of a. So we take the antiderivative, plug in the top bound, plug in the bottom bound, and then subtract the two. And that is all we have to do instead of using a Riemann sum. So the way this is going to break down is you're going to figure out what antiderivatives are first. Once you figure out what antiderivatives are, you're going to go ahead and talk about areas and different things like that. Once you do that, you're going to figure out how to put all of that mathematically into a Riemann sum kind of thing and evaluate those out, and those are going to be very tedious. I'm just going to warn you up front now, those are going to be not only difficult, but very long as well, so plan accordingly for that. Once you've been tortured enough by doing it that way, you'll learn about the fundamental theorem of calculus. You'll find an easier way that we can evaluate out those definite integrals. So that is the plan for this week. As always, I'm here if you have any questions. If you do, please feel free to email me or send me a message on Schoology or anything like that. I'd be happy to help out. And otherwise, have a great week and good luck.